September 14th, 1944, 0700 hours. Kummersdorf Proving Ground, Germany. Oberingenieur Klaus Brenner approached the wooden firing table where a single American rifle lay waiting for evaluation. The weapon appeared deceptively ordinary. Dark walnut stock, steel barrel, simple iron sights, 8 cartridges loaded in an en-bloc clip. To the untrained eye, it looked like any other infantry rifle produced by any other nation fighting this war. Brenner commanded the Small Arms Evaluation Section of Heereswaffenamt, the German Army Weapons Office. His team had been testing captured Allied weapons since 1941, cataloguing their capabilities, identifying weaknesses, recommending countermeasures. Soviet rifles, British rifles, French rifles, all followed predictable patterns. Bolt-action mechanisms requiring manual cycling between shots, clip-loading systems that demanded careful insertion, 5-round capacities that reflected conservative ammunition management. This American rifle was different. Intelligence reports from frontline units described impossible rates of fire. German soldiers claimed they were facing automatic weapons disguised as standard infantry rifles. Battalion commanders reported being overwhelmed by volume of fire that no conventional rifle should produce. The reports seemed exaggerated. Combat stress created false impressions. Frightened soldiers overestimated enemy capabilities. But the reports kept coming. From Normandy, from the Ardennes, from every sector where German infantry encountered American forces, always the same description: rapid, sustained fire from individual soldiers using what appeared to be standard rifles. The weapon on Brenner's table would answer those questions definitively. The M1 Garand had been recovered from the body of Staff Sergeant Michael Patterson, 1st Infantry Division, killed during the St. Vith fighting 3 days earlier. Patterson's rifle was intact, undamaged, loaded with 7 rounds remaining in the 8-shot clip. German intelligence officers had carefully preserved the weapon and its ammunition for technical evaluation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Brenner lifted the rifle and immediately noted its weight: 4.3 kilograms loaded, substantially heavier than the standard German Karabiner 98, which weighed 3.9 kilograms with 5 rounds. The extra weight suggested robust construction, possibly over-engineered by German standards where material conservation had become critical. The stock felt solid, dense American walnut that would resist warping in field conditions. The barrel measured 24 inches, standard length for infantry rifles, but the bore diameter was unusual, 7.62 millimeters, larger than the 7.92 millimeter rounds fired by German rifles. American ammunition philosophy apparently favored heavier bullets over higher velocities, a design choice that would affect ballistic performance and manufacturing requirements. Brenner's assistant, Hauptmann Friedrich Weiss, had prepared detailed firing tests using both American ammunition recovered with the rifle and German ammunition modified to fit the chamber. The testing protocol would measure rate of fire, accuracy, reliability, and mechanical durability under combat conditions. Standard evaluation procedures developed over 3 years of captured weapons analysis. The first test began at 0830 hours. Brenner shouldered the rifle and aimed at a target 100 meters downrange. The trigger pull felt crisp, breaking cleanly at approximately 3.2 kilograms of pressure, normal for military rifles. He fired the first round. The rifle cycled automatically. The spent cartridge case ejected forcefully. The bolt closed with authority, chambering the next round, without manual intervention. The entire action occurred in less than half a second. Brenner fired again. Same automatic cycling. Same rapid chambering. Same immediate readiness for the next shot. He continued firing in deliberate sequence. 3rd round, 4th, 5th, 6th, 7th. Each shot followed by instant automatic reloading. No bolt manipulation. No clip insertion. No manual cycling of any kind. Just pull the trigger, absorb the recoil, acquire the next target, fire again. The 8th and final round fired with a distinctive metallic ping as the empty en-bloc clip ejected automatically. The rifle's action locked open, visually indicating an empty chamber. Total elapsed time from first shot to empty chamber, 3.2 seconds. 8 rounds in 3.2 seconds from a weapon that weighed less than 5 kilograms and could be operated by a single soldier. Brenner lowered the rifle and stared at the chronometer. He had just witnessed something that challenged fundamental assumptions about infantry firepower. The German Karabiner 98, operated by an experienced soldier, could fire 5 rounds in approximately 12 seconds if the shooter rushed his bolt manipulation. The American rifle fired 8 rounds in 3 seconds while requiring no manual reloading between shots. The mathematical implications were staggering. A single American soldier armed with this weapon could deliver sustained fire at rates approaching light machine gun performance. 10 American soldiers could produce the volume of fire traditionally associated with a machine gun company. 100 American soldiers represented firepower equivalent to an entire German infantry battalion under ideal conditions. Weiss had been recording firing data throughout the test. His notes showed consistent cycling times between rounds of 0.4 seconds. The automatic reloading system functioned flawlessly with American ammunition. Accuracy remained acceptable throughout the rapid firing sequence. No mechanical failures, no ammunition feeding problems, no overheating despite the sustained rate of fire. The second test examined reload procedures under simulated combat conditions. Brenner inserted a fresh 8-round on-block clip into the rifle's internal magazine. The clip seated with an audible click indicating proper insertion. The loading process required approximately 2 seconds, including target reacquisition time. He fired 8 rounds rapidly, allowed the empty clip to eject automatically, inserted a fresh clip, and resumed firing. Total time between empty chamber and first shot of the next clip, 2.7 seconds. An experienced American soldier could theoretically maintain sustained fire with only brief interruptions for clip changes. The ammunition requirements became immediately apparent. Each rifle required specialized on-block clips that held 8 rounds in precise alignment for automatic feeding. The clips themselves were consumable items, ejected and lost after each firing cycle. American logistics systems had to manufacture and distribute millions of these clips in addition to the ammunition they contained. German ammunition production focused on cartridges loaded in standard clips that could be reused indefinitely. The American system accepted the logistical burden of disposable clips in exchange for superior rate of fire and reduced reload time. This represented a fundamental difference in manufacturing philosophy and resource allocation. Brenner examined the ejected on-block clip closely. Stamped steel construction, spring-loaded clip that held cartridges in exact spacing for reliable feeding. Simple design, but requiring precise manufacturing tolerances to function correctly. Mass production of these clips would demand significant industrial capacity dedicated to what German engineers would consider disposable components. The third test measured accuracy during rapid-fire sequences. Brenner fired 8 rounds at targets positioned 50, 100, and 200 meters downrange. Despite the rapid cycling and sustained firing rate, shot groupings remained within acceptable military accuracy standards. The rifle's weight and robust construction apparently dampened recoil sufficiently to maintain target tracking between shots. German rifles, while accurate, required deliberate shooting techniques to achieve comparable precision. The bolt-action mechanism forced shooters to break their sight picture between rounds, reacquire the target, and carefully align sights before firing. This process ensured accuracy, but severely limited rate of fire under combat conditions. The American rifle allowed shooters to maintain target focus throughout sustained firing sequences. The automatic cycling eliminated the sight picture disruption that characterized bolt-action rifles. Experienced marksmen could theoretically engage multiple targets in rapid succession without the mechanical delays that limited conventional rifle effectiveness. The implications for infantry tactics became immediately apparent. German doctrine emphasized careful marksmanship, ammunition conservation, and coordinated volleys that maximized the effectiveness of bolt-action rifles. American doctrine could emphasize rapid target engagement, suppressive fire, and individual initiative supported by superior mechanical rate of fire. By 09:45 hours, Brenner had fired 120 rounds through the captured rifle without mechanical failure. The weapon continued cycling reliably, despite sustained use that would have stressed most European designs. The barrel remained cool enough to handle without protection. The action functioned smoothly without additional lubrication. German small arms design philosophy prioritized mechanical simplicity and ease of manufacture. The Karabiner 98 represented mature bolt-action technology, refined through decades of military use. Simple, reliable, economical to produce, effective within its operational limitations. The American rifle represented a completely different approach to infantry weapons development, where German designers accepted the limitations of manual cycling in exchange for mechanical simplicity. American engineers had developed automatic systems that eliminated those limitations while maintaining reliability. The complexity was hidden within the rifle's action, invisible to the operator, but providing dramatic improvements in practical effectiveness. The fourth test examined the rifle's functioning with captured German ammunition modified to fit the American chamber. Brenner had anticipated feeding problems, extraction failures, or accuracy degradation when using non-standard cartridges. The rifle continued functioning normally, despite ammunition specifications that differed from original design parameters. This adaptability suggested robust engineering margins that allowed effective operation with various ammunition types. German weapons, while reliable, often required precise ammunition specifications for optimal performance. The American rifle appeared designed to function adequately, with ammunition that met basic dimensional requirements rather than exact specifications. The engineering philosophy reflected different manufacturing and logistics capabilities. German production emphasized precision manufacturing and exact tolerances to achieve reliable function with minimal material waste. American production apparently accepted looser tolerances and heavier construction to ensure function across wider operational parameters. Brenner's preliminary assessment identified capabilities that contradicted fundamental assumptions about infantry weapons development. The German army had optimized its tactics and logistics around bolt-action rifles that fired 5 rounds before requiring manual reloading. Training, doctrine, ammunition supply, and tactical formations all assumed rate-of-fire limitations that the American rifle simply ignored. The weight penalty that German engineers would consider excessive became acceptable when evaluated against firepower advantages. The manufacturing complexity that German industry could no longer support became practical when backed by American industrial capacity. The ammunition consumption that German logistics could not sustain became feasible with American supply systems. By 1000 hours, Brenner had completed initial evaluation protocols and begun drafting his preliminary report for Heereswaffenamt headquarters. The document would require careful language to convey the rifle's capabilities without creating panic among commanders already struggling with resource shortages and tactical reversals. The American rifle represented more than superior individual weapon performance. It embodied a different approach to infantry warfare that integrated mechanical advantage, industrial capacity, and tactical doctrine in ways that German planning had failed to anticipate. The implications extended far beyond small arms characteristics to encompass fundamental questions about military effectiveness and strategic sustainability. Weiss began preparing additional tests that would evaluate the rifle's durability under extreme conditions, its performance with various ammunition types, and its potential for modification or domestic production. But the initial results already suggested conclusions that would reshape German understanding of American infantry capabilities. The rifle that appeared ordinary to casual observation had revealed engineering sophistication and manufacturing quality that German industry could no longer match under wartime conditions. Every component showed evidence of precise machining, careful assembly, and comprehensive quality control procedures that reflected production capabilities beyond current German standards. October 2nd, 1944, 1400 hours, Heereswaffenamt Conference Room, Berlin. Oberingenieur Klaus Brenner stood before a table of senior officers presenting his comprehensive evaluation of the captured M1 Garand rifle. General Major Heinrich Müller commanded small arms development for the German army. His staff included representatives from ammunition production, infantry doctrine, and field logistics. The conference had been scheduled following distribution of Brenner's preliminary report 3 weeks earlier. That document had generated immediate interest and concern among commanders responsible for infantry effectiveness against American forces. The detailed evaluation that followed confirmed initial findings while revealing additional capabilities that challenged core assumptions about individual weapon performance. Mueller opened the briefing by reading casualty reports from units that had engaged American infantry during recent operations. Battalion commanders consistently described being overwhelmed by rates of fire that exceeded expected parameters for rifle-equipped soldiers. German casualties during firefights were rising disproportionately to engagement duration, suggesting fundamental changes in combat effectiveness rather than tactical modifications. The captured rifle sat on the conference table, where every attendee could examine its construction and operation. Brenner began his presentation by demonstrating the automatic cycling mechanism that eliminated manual bolt manipulation between shots. He inserted an 8-round en-bloc clip, fired the weapon safely into a sand-filled target box, and allowed participants to observe the automatic ejection and reloading sequence. The demonstration took 12 seconds from insertion to empty chamber. 8 aimed shots, delivered with mechanical precision, that required no special training or exceptional skill from the operator. Several officers requested personal demonstrations, firing the weapon themselves to understand its operational characteristics through direct experience. Oberst Werner Schmidt commanded infantry training for Army Group West. His units had been encountering American forces since the Normandy landings 4 months earlier. Schmidt reported tactical observations that aligned precisely with Brenner's technical analysis. American infantry sections demonstrated firepower density that German doctrine had never anticipated from rifle-armed soldiers. Traditional German infantry tactics assumed that rifle fire would be deliberate, aimed, and limited by manual reloading requirements. These assumptions shaped formation spacing, advanced techniques, and defensive positioning that optimized protection against conventional bolt-action weapons. The American rifle made these tactical adaptations inadequate or dangerous. Schmidt described engagements where individual American soldiers had suppressed entire German squads through sustained rapid fire that prevented effective return fire or tactical movement. The volume of incoming rounds created psychological pressure that degraded German soldier effectiveness, even when casualties remained moderate. The logistics implications became apparent when Oberst Friedrich Weber presented ammunition consumption data from captured American supply records. American infantry units were allocated ammunition quantities that exceeded German standards by factors of 3 to 5. Individual soldiers carried basic loads that German logistics considered excessive for sustained operations. The M1 Garand's 8-round capacity and rapid reloading capability enabled American soldiers to expend ammunition at rates that would exhaust German basic loads within minutes of sustained engagement. This consumption pattern required supply systems capable of delivering massive ammunition quantities to forward positions continuously throughout extended operations. Weber calculated that equipping German infantry with comparable rifles would require tripling current ammunition production, while simultaneously redesigning logistics systems to handle increased transportation and distribution requirements. These modifications exceeded current German industrial capacity and resource availability under wartime constraints. The manufacturing analysis presented by Oberingenieur Hans Richter revealed production challenges that reinforced logistical concerns. The M1 Garand required machining tolerances and assembly precision that German small arms factories could no longer maintain consistently. Specialized tooling, skilled workers, and quality control procedures necessary for reliable automatic operation exceeded current German manufacturing capabilities. Richter estimated that domestic production of comparable rifles would require 18 months of factory retooling, extensive worker retraining, and raw material allocations that would reduce production of other critical weapons systems. The opportunity costs made such conversion impractical, given strategic priorities and resource limitations facing German industry in late 1944. The automatic cycling mechanism that provided the rifle's primary advantage depended on precise gas pressure management, timing, coordination, and component durability that required advanced metallurgy and engineering expertise. German engineers understood the principles, but lacked the industrial infrastructure to implement mass production without compromising existing production programs. Brenner's detailed technical analysis identified specific components that exceeded German manufacturing standards. The rifle's barrel required specialized steel alloys and heat treatment procedures that German industry had never mastered completely. The gas system demanded precision boring and careful assembly that increased production time and quality control requirements significantly. The en-bloc clip system presented additional manufacturing challenges that affected both the rifle and its ammunition supply. Each clip required stamped steel components manufactured to exact specifications for reliable feeding and automatic ejection. Mass production demanded dedicated tooling and consistent quality control that German industry could not support without reducing other production priorities. American logistics systems absorbed the complexity and cost of disposable clips as an acceptable trade-off for enhanced battlefield effectiveness. German logistics, constrained by resource shortages and transportation limitations, could not afford such disposable components without fundamental reorganization of supply priorities and distribution systems. The conference discussion revealed broader implications that extended beyond individual weapon capabilities to encompass systematic differences in military development and industrial support. The American rifle represented integrated design thinking that combined mechanical engineering, manufacturing capability, and tactical doctrine into comprehensive solutions that German planning had failed to achieve. Müller summarized the strategic situation that made effective response difficult, despite complete understanding of American advantages. German industry was producing maximum output under current constraints, but could not expand production or introduce new systems without reducing existing weapon deliveries. Any modifications to small arms production would decrease availability of rifles, machine guns, and ammunition that frontline units required immediately. The tactical recommendations developed by Schmidt's staff emphasized modifications to German doctrine that might reduce American firepower advantages without requiring new equipment or extensive retraining. These adaptations included revised formation spacing, improved use of cover and concealment, and coordination techniques that maximized German strengths while minimizing exposure to rapid American fire. The proposed changes represented significant departures from traditional German infantry doctrine that had emphasized aggressive tactics and close-quarters engagement. The new approaches accepted defensive postures and cautious movement that contradicted core principles of German military culture while acknowledging tactical realities imposed by superior enemy equipment. Training modifications would require extensive revision of infantry manuals, instructor retraining, and prolonged practice periods that German replacement training systems could not support given accelerating casualty rates and shortened training cycles. Implementation would occur gradually through unit-level adaptation rather than systematic doctrinal revision. The psychological impact of technological inferiority became apparent during discussion of soldier morale and combat effectiveness. Units that had engaged American forces equipped with automatic rifles reported declining confidence in their own weapons and tactics. German soldiers understood that they were confronting enemies with superior individual firepower, backed by superior logistics systems. This recognition undermined the aggressive spirit that German doctrine required for battlefield success. Soldiers who expected to outshoot their opponents through superior marksmanship and tactical skill found themselves outgunned by enemies, using mechanical advantages rather than exceptional training or experience. The disparity created defensive mentalities that reduced initiative and tactical flexibility among German units. Commanders reported increasing reluctance among experienced soldiers to engage American forces under circumstances where German weapons and tactics had previously provided advantages. October 15, 1944, 0800 hours, Kummersdorf Proving Ground, Germany. Oberingenieur Klaus Brenner supervised extended durability testing designed to evaluate the captured M1 Garand's reliability under extreme operational conditions. The initial evaluation had revealed impressive capabilities, but combat effectiveness required sustained performance through thousands of rounds, adverse weather, and minimal maintenance conditions. The durability tests would simulate 6 months of intensive combat use, compressed into 3 weeks of controlled evaluation. Brenner's team would fire 5,000 rounds through the rifle, while subjecting it to temperature extremes, moisture exposure, dirt contamination, and mechanical stress that exceeded normal battlefield conditions. Hauptmann Friedrich Weiss had designed test protocols based on captured American field manuals that described maintenance procedures and operational limitations. These documents revealed design margins and expected service life that provided insights into American engineering philosophy and manufacturing quality standards. The American technical manuals specified maintenance intervals and replacement schedules that assumed sustained high-volume usage over extended periods. Component life expectancies exceeded German standards for comparable parts, suggesting either conservative design margins or superior materials and manufacturing processes. The first phase of durability testing examined mechanical wear under sustained firing conditions. Brenner's team fired 1,000 rounds in rapid sequence, allowing only brief cooling periods between firing cycles. The rifle maintained reliable function throughout this stress test, despite barrel heating and increased fouling that would have degraded most European designs. The automatic cycling mechanism continued operating smoothly, despite carbon buildup and powder residue that accumulated within the gas system. The precise timing that enabled reliable automatic operation remained consistent throughout extended firing cycles. No mechanical adjustments or intensive cleaning procedures were required to maintain function. German rifles required frequent cleaning and careful maintenance to preserve accuracy and reliability during sustained use. The bolt-action mechanism provided simplicity, but demanded regular attention to prevent fouling-related malfunctions. The American rifle's automatic systems proved more tolerant of operating conditions that would compromise conventional designs. The second phase evaluated performance under environmental stress that simulated European winter conditions. The rifle was exposed to temperatures ranging from -20 degrees Celsius to +40 degrees Celsius, while cycling through humidity variations and precipitation that tested material stability and mechanical tolerance. Throughout these environmental tests, the rifle continued functioning reliably, with minimal performance degradation. The wooden stock maintained dimensional stability despite moisture variations that would warp European hardwoods. Metal components showed no corrosion or dimensional changes that affected mechanical operation or accuracy. American manufacturing apparently employed wood treatment and metal finishing processes that exceeded German standards for environmental resistance. The rifle's components were designed and built to function effectively across operational parameters wider than those typically encountered in European combat conditions. The third phase examined dirt and contamination resistance through systematic exposure to sand, mud, and debris that would accumulate during combat operations. The rifle was partially disassembled, contaminated with various materials, reassembled, and tested for continued operation without intensive cleaning procedures. The automatic cycling mechanism proved remarkably tolerant of contamination that would disable most precision machinery. Dirt and debris that accumulated within the gas system were expelled automatically during normal operation without manual intervention or special maintenance procedures. This self-cleaning capability reduced maintenance requirements under field conditions. German weapons required careful cleaning and protection from contamination to maintain reliable function. Precision tolerances that enabled accuracy and mechanical reliability also created vulnerability to dirt, moisture, and combat debris. The American rifle achieved comparable precision through robust design that maintained function despite contamination. By November 1, 1944, the captured rifle had fired 4,700 rounds with only 2 minor mechanical failures that were corrected through simple maintenance procedures described in captured American field manuals. Component wear remained within acceptable limits for continued service, despite stress levels that exceeded normal combat usage. The barrel showed minimal erosion despite firing ammunition types that differed from original specifications. Accuracy remained within military standards throughout the testing period. The automatic cycling mechanism maintained consistent timing and reliable operation without major adjustment or component replacement. These durability characteristics reinforced conclusions about American manufacturing capabilities and design philosophy that had emerged during initial technical evaluation. The rifle represented mature engineering solutions backed by production quality that German industry could no longer match under wartime constraints. Brenner's final technical report documented performance characteristics that established the M1 Garand as the most effective individual infantry weapon encountered during comprehensive testing of captured Allied equipment. The rifle's combination of rapid-fire capability, mechanical reliability, and operational durability exceeded German standards across all evaluation criteria. The report's conclusions confirmed tactical observations from frontline units, while providing technical analysis that explained American infantry advantages through superior equipment rather than exceptional training or tactical innovation. The disparity was systematic rather than temporary, reflecting industrial capacity and engineering expertise that would continue producing technological advantages throughout the war's remaining phases. The manufacturing recommendations included in the final report emphasized impossibility of domestic production, given current German industrial constraints and strategic priorities. The engineering complexity and production requirements exceeded available resources while offering uncertain benefits, given the war's strategic trajectory and timeline for potential implementation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The captured rifle was transferred to training facilities, where it continued serving demonstration requirements for units preparing to engage American forces. The weapon provided valuable tactical intelligence about enemy capabilities while serving as tangible evidence of technological disparities that were reshaping battlefield effectiveness across all theaters. Intelligence reports incorporating Brenner's technical analysis reached field commands throughout November and December 1944. These documents provided detailed information about American rifle capabilities, while recommending tactical modifications that might reduce German disadvantages without requiring new equipment or extensive retraining programs. The broader implications of American small arms superiority extended beyond individual weapon performance to encompass systematic advantages in industrial capacity, design, philosophy, and logistics support that characterized American military effectiveness across multiple equipment categories. The rifle represented one example of comprehensive technological advantages that German planning had failed to anticipate or counter. December 7, 1944, 1600 hours. OKH Field, Headquarters, Ziegenberg, Germany. Generaloberst Heinz Guderian studied intelligence summaries describing American equipment advantages identified through systematic evaluation of captured weapons and supplies. The reports painted a comprehensive picture of technological and industrial disparities that challenged core assumptions about German military effectiveness. The M1 Garand rifle analysis was included alongside similar evaluations of American tanks, artillery, communications equipment, and logistics systems. Each assessment reached similar conclusions about superior manufacturing quality, advanced design solutions, and production capabilities that exceeded German standards while meeting higher performance requirements. Guderian understood that technological disparity reflected broader strategic problems that extended beyond individual equipment characteristics to encompass fundamental differences in industrial capacity, resource allocation. The American rifle represented one manifestation of systematic advantages that characterized enemy capabilities across all weapon categories. The tactical intelligence gathered through captured equipment analysis confirmed observations from frontline commanders who reported increasing difficulty maintaining defensive effectiveness against opponents equipped with superior weapons and supported by superior logistics systems. German units were fighting with declining equipment quality while confronting enemies with improving capabilities. The strategic implications became apparent when ammunition consumption data from American units was compared with German production and supply capabilities. American infantry consumed rifle ammunition at rates that exceeded total German small arms ammunition production for entire army groups. This disparity made sustained defensive operations increasingly difficult. German ammunition production had peaked in mid-1943 and declined steadily thereafter due to raw material shortages, bombing damage to production facilities, and diversion of resources to other strategic priorities. American production continued expanding throughout 1944, while maintaining quality standards that German industry could no longer achieve consistently. The resource calculations that emerged from comprehensive equipment analysis revealed strategic limitations that tactical modifications could not overcome. Germany lacked the industrial capacity to match American production, while simultaneously maintaining current weapons output and developing new systems required for technological competition. The manufacturing infrastructure necessary to produce comparable weapons would require extensive retooling, substantial raw material commitments, and skilled worker training programs that exceeded available resources, given immediate military requirements and strategic timeline constraints. These investments could not be recovered before the war's likely conclusion. Guderian's assessment incorporated intelligence about American industrial capacity that suggested continued technological advancement rather than stabilization at current levels. American factories were developing improved weapons, vehicles, and systems that would further increase capability gaps throughout 1945 and beyond. The captured M1 Garand represented mature American technology from 1943 production runs. Intelligence indicated that newer versions incorporated improvements in manufacturing quality, component durability, and operational effectiveness that would make the capability gap even larger during 1945 operations. The strategic implications of systematic technological inferiority extended beyond immediate battlefield effects to encompass psychological factors that influenced German soldier effectiveness and unit cohesion. Troops who understood their equipment disadvantages fought differently than soldiers confident in their weapons and tactics. The reports from units equipped with captured American weapons revealed significant morale improvements when German soldiers could access superior equipment taken from enemy forces. These psychological effects confirmed that technological disparity was affecting combat effectiveness beyond the direct impact of equipment performance differences. German soldiers using captured M1 Garand rifles reported dramatically improved confidence in firefights against American forces. The superior rate of fire and reliability enabled aggressive tactics that German rifles could not support effectively. These experiences demonstrated the tactical advantages that superior individual weapons provided to ordinary soldiers. But captured weapons could not provide systematic solutions to technological inferiority, given limited availability and ammunition supply problems. German units might capture individual rifles, but could not obtain the ammunition, spare parts, and maintenance support required for sustained operations with American equipment. The logistics analysis revealed that American weapons effectiveness depended not only on superior individual performance, but comprehensive support systems that German logistics could not replicate. Ammunition supply, maintenance procedures, and replacement parts were integrated into comprehensive systems that supported sustained operations with minimal degradation. German weapons and logistics had been designed around different performance parameters and operational assumptions that reflected resource constraints and industrial limitations present since the war's beginning. These systems could not be modified quickly to accommodate American performance standards without fundamental reorganization. The final assessment, prepared for higher command levels, emphasized that technological inferiority was symptom rather than cause of broader strategic problems affecting German military effectiveness. Superior enemy equipment reflected superior industrial capacity, advanced engineering expertise, and resource allocation that Germany could not match under current circumstances. The recommendations focused on tactical modifications and strategic adaptations that might reduce American advantages through improved German doctrine and operational techniques, rather than equipment replacement or technological terrorized competition that exceeded available capabilities and resources. These modifications represented acceptance of technological inferiority as permanent rather than temporary condition that required adaptive responses rather than direct competition. German forces would fight with existing equipment, using modified tactics that minimized exposure to American advantages, while maximizing traditional German strengths in training and tactical flexibility. The psychological preparation for technological inferiority included revised training, programs that emphasized equipment limitations, while building confidence in tactical skills and unit cohesion that could compensate for mechanical disadvantages. Soldiers needed realistic understanding of their weapons' capabilities while maintaining motivation for continued resistance. January 12, 1945, 0900 hours. Oberingenieur Klaus Brenner sealed his comprehensive technical analysis of the captured M1 Garand rifle and prepared final documentation for historical record. The evaluation had consumed 4 months of detailed testing, analysis, and reporting that provided complete understanding of American small arms capabilities and their implications for German defensive operations. The technical specifications documented through systematic testing revealed engineering solutions that exceeded German manufacturing capabilities while providing battlefield advantages that German tactics could not effectively counter. The rifle represented mature American military technology that reflected systematic advantages in industrial capacity and design philosophy. The final report included detailed manufacturing analysis that documented production techniques, quality control procedures, and material specifications that enabled reliable automatic operation under combat conditions. These manufacturing capabilities exceeded current German standards while suggesting continued improvement in American industrial processes. The durability testing results confirmed that American rifles were built to performance standards that assumed sustained high-intensity usage over extended periods. Component life expectations, maintenance intervals, and environmental tolerance exceeded European standards while maintaining precision and reliability that German weapons could not match consistently. The tactical implications, summarized in concluding sections, emphasized rate-of-fire advantages that provided American infantry with firepower density, equivalent to light machine gun units, while maintaining individual weapon mobility and tactical flexibility. These advantages transformed infantry combat dynamics in ways that German doctrine had not anticipated. The strategic assessment acknowledged that technological disparity reflected broader industrial and resource advantages that Germany could not overcome through equipment development or production modifications given available capabilities, and timeline constraints. The rifle represented one example of systematic American superiority across multiple technology categories. The historical context provided in the final analysis placed the M1 Garand within broader patterns of American military development that prioritized mechanical solutions to tactical problems, accepted manufacturing complexity in exchange for battlefield effectiveness, and integrated industrial capacity with strategic planning to achieve comprehensive technological advantages. The captured rifle continued, serving training and demonstration requirements through the war's final months, providing tactical intelligence about enemy capabilities while serving as tangible evidence of technological competition that had determined strategic outcomes before major battles were fought. The weapon became symbol of industrial warfare, where manufacturing capacity proved as decisive as tactical skill. For German engineers and military planners, the M1 Garand evaluation provided comprehensive case study of how technological development, industrial capability, and strategic resource allocation combined to create military advantages that tactics alone could not overcome. The rifle represented lessons about systematic preparation and long-term planning that extended beyond immediate military applications. The broader implications of American technological superiority became apparent during final months of warfare, as German units encountered additional advanced weapons systems that reflected similar design philosophy and manufacturing capability. Each new system confirmed patterns identified during rifle evaluation, while demonstrating continued American advancement. The strategic reality that emerged from comprehensive equipment analysis was clear and unavoidable. Germany had lost the technological competition that underpinned modern warfare before major campaigns began. Industrial capacity, engineering expertise, and resource allocation had determined outcomes that battlefield tactics could influence, but not reverse. The M1 Garand rifle, recovered from Staff Sergeant Michael Patterson's body near St. Vith in September 1944, had revealed strategic truths that extended far beyond small arms characteristics. In the hands of German engineers, the weapon became instrument of strategic revelation rather than tactical intelligence. 8 rounds in 3 seconds, automatic cycling, reliable operation, robust construction, industrial quality. These characteristics represented more than superior individual weapon performance. They embodied comprehensive American approach to military problem-solving that integrated technology, manufacturing, and logistics into systematic advantages that German planning had failed to anticipate or counter effectively. The rifle that appeared ordinary during casual observation had demonstrated engineering sophistication and production quality that German industry could no longer match under wartime conditions. Every component revealed precision manufacturing, careful assembly, and quality control procedures that reflected industrial capabilities beyond current German standards. For Klaus Brenner and his evaluation team, the captured M1 Garand had provided professional education in advanced military technology while serving as stark reminder of strategic realities that no amount of tactical skill could overcome. The weapon represented both American achievement and German limitations within broader context of technological competition that had shaped warfare's trajectory since industrial mobilization began. The rifle's final disposition reflected broader patterns affecting captured equipment throughout Germany's declining strategic position. Used for training until ammunition supplies were exhausted, then preserved as historical artifact, documenting technological disparity that characterized conflict's final phases. Physical evidence of industrial warfare where production capability proved as important as battlefield courage. For families of soldiers who encountered American rifles during combat operations, the technical analysis provided context for tactical challenges that individual units had faced without understanding broader strategic implications. The weapon represented systematic problems rather than isolated disadvantages, technological competition rather than temporary setbacks. The engineering lessons learned through M1 Garand evaluation would influence post-war military development as surviving German engineers applied technical knowledge gained through systematic analysis of superior American equipment. The rifle became educational tool that demonstrated integration of design philosophy, manufacturing capability, and tactical doctrine into comprehensive military effectiveness. The final irony was that complete technical understanding of American rifle capabilities had arrived too late to influence strategic outcomes or tactical adaptations that might have reduced German disadvantages. The weapon's secrets were revealed when German industry could no longer apply such knowledge effectively, when resource constraints prevented implementation of competitive responses. 8 rounds in 3 seconds had represented more than rate of fire advantage. It embodied systematic American superiority in industrial capacity, engineering expertise, and strategic planning that had determined warfare's outcome before decisive battles were fought. The captured rifle had provided window into technological competition that shaped modern conflict while demonstrating limitations of tactical excellence without strategic resources. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.